So the first step. The first step, oops, is not really a design step, it's more an interpretation step. So we started with the application description of the active antenna, and usually you start with some kind of description of the product you need to make, the amplifier you need to make. And we have to translate this specification coming from someone, from somewhere, into things that we can work with. And we have seen that we split such a specification in functional specifications, performance specification, and specification of cost factors and environment. In the bachelor course, we did this all with slide cap. In this course, we didn't pay much attention to it because it wasn't basically new. We already did it with slide cap. But of course, we still have to derive all the specifications from the description. So for the active antenna, that means we have the description, and what we need to know is the functional requirements to start with. So what functions are required? In this case, it was mainly amplification function. And for the amplifier that we discussed the design here, we need to know port impedances and the source to load transfer. That is basically what we want to know. And all this will be described later with the parameters, the matrix transmission 1 parameters A, B, C, and D. So then there must be a transfer from source, from the antenna to the load, and we want to know what is the quality of the information transfer and what should be the capacity of the information transfer. So how much information, and we know it is limited by this channel capacity thing from Shannon, like bandwidth and noise and maximum power level, but also the quality, the signal to noise ratio. We want to know some more details about the weak nonlinearity, inaccuracy, maybe temperature behavior. So what is the quality of the information processing? I just put up a few things here. Noise. Everything we don't want, we call noise. That is the general way of defining noise. So it's not only thermal noise, but also, for example, offset drift can be regarded as noise. But let's say in many situations, typically in this situation with the active antenna, we are dealing with frequencies of interest that are much higher than the frequencies where we have temperature variations. So let's say we don't have to pay much attention to this topic here, but if you want to make so-called DC or low frequency amplifiers, it can be very important to take this in consideration. The static and dynamic signal handling capability, so how much voltage and how much current should be delivered to the load, that is what we should know. The inaccuracy, and that's including all kind of effects due to aging or temperature drift, then related to the gain. The frequency or time domain response, we basically went for a maximally flat frequency response in many cases, but that is not always required. Weak nonlinearity, it can be specified in various ways: harmonic distortion and intermodulation distortion. Intermodulation or gain compression can be another effect, or just nonlinearity. We have discussed all these kind of definitions in the bachelor course. Cost factors, what is the price we are willing to pay for the solution, and for example, in this case, the operational costs. So what is the supply voltage we have available, the current consumption, what is allowed, the dimensions, and what are the operating conditions. This refers to temperature range, interference, and electromagnetic and electrostatic discharge. So let's have a little bit a look at the antenna specification and see what we can find from there, if we can make it complete. That's what we did basically. So the next is here. Maybe you remember this picture. This was our assignment. We needed to make the active antenna. That what the antenna itself was a capacitive rod, and the active antenna should drive a long cable, a 50 ohm cable, and the rest that is there on the right is just for the contacts, but we didn't pay any attention to it for the rest during the design. So let's put together all the performance aspects. We have found a specification of the maximum RMS input signal in volts per meter. So using the length of the antenna, we could convert this in input voltage for the amplifier. We have found the corresponding maximum output voltage across a 50 ohm load. We have specifications for the antenna referred noise in the sense of spectral densities that were allowed at different frequencies. Output impedance, because the cable was very long, we needed to drive it with its characteristic impedance, so the output impedance would be 50 ohm. The frequency range of interest, something like 10 kilohertz to 30 megahertz, if I remember well. The response type, and here I think this wasn't really specified, but we assumed maximally flat magnitude response, frequency response. IMD, I remember minus 50 dB IM components, in-band IM components. The costs, they were not all specified very clearly, so I just list a few so that you can use it for future designs. You have a kind of checklist, and there can be in specific designs many other types of cost that might be relevant. So in this case, we have antenna length. We were designing the amplifier with 50 centimeters antenna length. The supply voltage, the power consumption that was specified, the dimensions. Well, this is not very interesting for a chip. Then we more speak of technology, external components and package. So external components is what you need on the PCB, because this is also, of course, space might be space consuming. In many cases, you don't want external components, only if really necessary we need to. Operating conditions, temperature range, EMI, and ESD. ESD was not specified. There should be some kind of human body model specification for this. EMI was also not specified. We keep it out of this course, but in general, it is relevant, and you have to design for out of band, often EMI components, noise